Okay, so today and the next time we'll finish this. I'm going to start talking about expanding analysis of variance into something much more powerful. Now, when you do this stuff, and I'll eventually show you how to do it with SPSS, you don't use the compare means function anymore. You use something called the GLM, General Linear Model. It's actually doing the same thing. Okay, but you don't use the compare means function. Okay. As an aside, generally when you're setting up a data set, you want a subject number, whatever that subject is, 1, 2, 3, 4, 5, just give a number. The independent variable level, so A1, A2, A3, whatever, and then the dependent variable. Each of those is a record, it'll always work. Okay, so yeah, I made up some data. Let's pretend we're doing just a memory experiment, standard memory experiment. We're going to give people lists of words, and we're going to get percentage correct. And let's say you've collected data on the effects of retention interval on memory. This is not going to be anybody's honors thesis. This was figured out a long time ago at Ebbinghaus, 1890. So you don't have to, ooh! And this is not that different than numbers you might get, but 90% correct after 5 minutes, 70% correct after an hour, and maybe down to 60 or even less perhaps after 24 hours. Okay? So it wouldn't be a surprising result. We would do an analysis of variance, and we conclude that retention interval affects memory. You might do post hoc tests. In this case, you might do a transformation on those data because they're proportions, percentages, if the variances are messed up. But you'd end up concluding retention interval affects memory. It would be nothing groundbreaking. You would be the zillionth person to replicate that result. Now, let's say you tried to do something else. You thought it was the levels of processing. Those of you who have taken memory with me or are taking it with me know about levels of processing. It's the idea that we have different levels of how deep we process items when we remember them. Starting at a low level, which is just what something looks like, just a pattern of let's say it's words again. So it could be the number of ascending and descending letters. So if one of the words was, well, let's go with levels here, it has 2 ascenders. Okay? So I'm just asking you to count the number of ascending and descending letters. Middle level might be how many syllables are there, because you have to kind of read the word out to yourself to figure that out. So the word levels, got 2 levels. I could have you counting phonemes, but you probably make mistakes if you think too much about it. We'll do that. And finally, I can have you rate the pleasantness of the word on a scale of 1 to 7. Now you think about the meaning of the word. Right? And you think levels, isn't that pleasant a word? No, or unpleasant, I don't think. But the point is, you have to think about what the word levels means to go on. So that's going to be more deep processing, more high level of processing. And you'd get something like that. Right? Levels of processing effect is, again, the paper on levels of processing is the most cited paper in the history of comparative psychology. Or, cognitive psychology. Probably experimental psychology. Craig and Lockhart, 1972. It's been cited 12,999 times. Or something like that. 12,299 last week when I checked, just before I gave a lecture on this. It's probably more already. It goes up about 2,000 a year. It's pretty good. So you do an ANOVA and you conclude the levels of processing affects memory. Again, you will not win any Nobel Prizes or even get credit for designing a thesis project because this is too easy. It's a neat idea. It was also discovered when I was 8 years old. Great. What level of retention interval should you have done your levels of processing for the experiment at? So you should have 5 minutes, 1 hour, 24 hours, 2 weeks, 10 seconds? Or for that matter, what level of processing should you have used for your retention interval experiment? Should you have told people to read the word for themselves aloud? Should you have told people to count the number of syllables? Right? So what are you supposed to do? Are we supposed to try it at all the different levels of retention interval? At all the different levels of processing, which is a horrible... I should start using a different example. The slides are made up. I'm not changing them. Yeah, that's probably true. Well, what we do, of course, is we're going to combine them. So we're going to get groups of subjects, group 1, group 2, group 3, 4, 5, 6, 7, 8, 9. Okay? Oh, the music's starting again? There's one year when I was teaching brain behavior in that room over there, if you remember, where they would always sort of play piano during the class. It was the weirdest thing. And one day he started playing, like singing in the rain, and I kid you not, there was an umbrella sitting there. And we left, and I just took it a little. That's all the dancing I do until you get about 15 beers in me. Just keep that in mind. Dancing is just before karaoke for me. So what we have here, we call it a 3x3 design. Between subjects factors, both of them, we call it a 3x3 between subjects design, we call this, or a 3x3 factorial. What you've done is you've combined every level of retention interval and every level of levels of processing. So now you have 9 groups, not just 3. You've basically done, you're testing both of these variables at the same time. Exceedingly common approach. Question so far? Do you understand the setup? Okay, good. So here comes the model. This is the structural model. Lit on fire first, which was good. I probably like that. X equals mu plus alpha plus beta plus alpha beta plus epsilon. And those alphas and betas aren't the same as type 1 and type 2 error. I'm sorry, it's not my fault. I didn't develop the freaking notation. Don't get mad at me, get mad at someone else. I don't know. I don't know who we can blame, but somebody we all hate. I don't know who that is. I don't think we would probably come to some Hitler. It was Hitler's fault. That's what it is. We'd probably come to a general agreement that he was a bad guy. It was probably Hitler's fault. Any score, sometimes I get bored and I play with the transition things, I'm sorry, equals the grand mean plus the A effect plus the B effect. That's independent variable A, independent variable B. There are 2 variables, A and B. In this case, we can say A was the levels of processing and B is the retention interval, if you want. The A-B interaction, and of course, that's fast, right? That comes in pretty good. Error. Individual differences, stuff left over. X equals mu plus alpha plus beta plus epsilon. Say that yourself 3 times before you go to bed, and Fisher appears and kills you. It's more like Candyman, isn't it? It's a mirror. R.A. Fisher, R.A. Fisher, R.A. Fisher. And then an old biologist appears behind you and develops these things from first principles. Much more boring. But better. Okay. So X equals mu plus alpha plus beta plus epsilon. Ooh. Oh, I thought, was that a slide? Was that a slide, didn't it? I screw around with these things enough because, no, I don't correct or change the examples. I just start playing with transitions because I'm a loser. And it gets to the point, it's like, oh, my whole presentation's wrecked. So, not only can we look at the effects of A and B on their own, because this is going to isolate the effect of A and ignore the effect of B. The math will do that. It's going to isolate the effect of B and ignore the effect of A. So those are great. But we also look at how they act together or how they interact. Sort of a whole is more than the sum of its parts thing. Right? So the whole is more than the sum of its parts. This is the effect of one variable changing depending upon the level of a second variable. That's in fact definitionally what what's called a two-way interaction is. the effect of one variable changes depending upon the level of some second variable. So, I mean, you can think of it this way. I always can only think of sad examples. But let's look at income. Women make less money than men. Not good, but it is. That gap's getting smaller, but it's still there. Women make less money than men. Right? So if we were to predict income based on your sex, you make less money if you're a woman. Okay. Native people make less money than white people. It's not good, it just is. The world is getting better that way, but there's still that big. But being a native woman is probably harder than just being native or just being a woman. It's probably, in fact, it's probably something that adds on to that. There's an extra thing. Right? So that's an interaction. We could make it happy and say it's great being a white man, but that wouldn't be very cool to say. So it's this extra effect. Something over and above just the sort of additive effect of some level of A and some level of B. Okay. Now that we're all depressed, let's look at this. It's like this. We have an experiment. These are some results of, I don't know what the hell it is. I have no creative skills whatsoever. But we can pretend that we have an experiment here where we have some results. There's group A, there's A1, level A1, and level A2. This is B1, and this is B2. You can see that at A1, B2 is bigger than B1 by, it looks like, 2 points. That looks like 5 and 7, right? And over here at A2, B2 is that about 12 and that's 20, is 8 bit points bigger. The effect of B changes depending upon the level of A. It's a bigger effect at A2 than it is at A1. Okay. Does this make sense so far? I don't know why that's like that. Anyway, doesn't matter. The difference between B1 and B2 is smaller at A2 than it is, it should say, at A1. The effect of B changes depending upon the level of A. I screwed around with things, obviously screwed that up. One of the sort of rules of thumb you can use is, are the lines parallel? If they're not parallel, you maybe have an interaction. All right. So x equals mu plus alpha plus beta plus alpha, beta plus epsilon. We have assumptions that are built into the model. The sum of the alphas, the alpha i's equals 0. What does that mean? That means the elevation or depression due to the level of A that you have. Let's say if you're in group, if you're level 1 of A, so you're at A1, your score goes up by 2. And if you're at A2, your score, and let's say we only got a 2 by 2, so A1, A2, B1, B2, your score goes down by 2. Okay. So the sum of the alpha i's, I is just an index. So A1 you go up to, A2 you go down to. It has to sum to 0. And you'll see in a bit that that just falls out of this working this way. There's no other way this can work. Okay. The sum of the beta j's equals 0. So the sum of the B effects equals 0. So if B1 makes you go up 7, B2 makes you go down 7. Okay? The sum of the alpha I beta j's, the effect of being A1, B1, A1, B2, A2, B2, A2, B1, I think I got them all there, sum to 0. So if it was like this, so A1, A2, B1, B2. A1, let's say this A1, B1 makes you go up by 1. A2, B1, you go down by 1. A1, B2, you go down by 1. A2, B2, you go up by 1. There's a special little thing there that they have to sum to 0, but they actually also have to sum to 0 in rows and columns. Okay? So they have to, going down, going across, they have to also sum to 0. And again, you'll see in a second when I work through a couple of examples that there's no other way this can work. This isn't, this actually falls, these things actually come out of the fact that you're saying this is true. Okay? And if you remember, the sum of the tau effects, the treatment effects, always sum to 0 in the original analysis variance, the sort of plain one-way analysis variance. The sum of the treatment effects, the sum of the tau, T treatment 1, treatment 2, also sum to 0. These are just treatment effects. We just have now 2 treatments. And then we have this extra thing, this interaction term. Error is normally distributed and independent with a mean of 0 and a variance of sigma squared. Okay? So the error is normal and independent with a mean of 0 and a variance of sigma squared. It's the same thing with individual differences we had in the one-way analysis of variance. Error is normal and independent with a mean of 0 and a variance of sigma squared. You can violate the normality. You can't violate the independence. And the 0 and sigma squared, again, just follow the fact that we said at the beginning that x equals u plus alpha plus beta plus alpha beta plus epsilon. You'll see. Okay. Those are some assumptions that come out of the model. We're going to do an F-test. We're going to do a couple, actually 3 F-tests. We're going to see if A is significant, independent variable A, is independent variable B significant, and is the interaction significant. So let's look at some assumptions for an F-test. Homogeneity of variance, not surprising. This is just analysis of variance, just a little more complicated. Random samples. Sure they are. Close enough. You can violate that. You can violate that. We never have random samples. It never happens. Right? But it's not a big deal. Normal populations. Doesn't matter. Violate the hell out of that. Doesn't matter. So most of the F assumptions we can violate. We can violate this to a point, homogeneity of variance. We almost always violate random samples and normal populations, and it just doesn't matter. Okay? The math doesn't change that much. Yeah, Sean?
Is the violation for homogeneity of variance still 4?
Yeah, it's like the sort of rule of thumb is 4 times bigger than another. Yeah. And that's just a rule of thumb. I mean, all it does when you violate homogeneity of variance is it makes the tests more conservative. So the nice thing is it makes it less likely for you to find an effect that's there. It doesn't make you more likely to say there's an effect that isn't there. Which is good, because at least you're going to miss something, which, too bad you missed it. But you're not going to say, there's aliens and psychics. Like, you're not going to say something ridiculous. Right? You're not going to say, oh, there's an effect when there isn't one. It's not going to do that, at least. If it made the test unreliable that way, we'd probably find a new way to analyze data. Good question. Okay, let's look at sort of a numerical example. These are going to be means, group means. I'm going to ignore individual subject scores within each cell. So let's just say that there's 5 people in each cell and their mean is 9 for A1, B1. and their mean is 7 for A2B1, and their mean is 3 for A1B2, and their mean is 1 for A2B2. Okay? So I'm ignoring that there's individuals in there. I just want to look at group means for illustrative purposes. Okay. Questions? You see what I've done then? That's all this is. These A is an independent variable and B is an independent variable. I don't know what they are. They're A and B. Okay, that's all they are. Okay, remember that x equals mu plus alpha plus alpha beta plus epsilon. Let's take out all these different components. And let's go from the most general thing to the more specific thing. So the most general thing is the grand mean. Well, what's the grand mean? 9 and 7 is 16, and 3 is 19, and 1 is 20 divided by 4, because there are 4 cells, is 5. There's nothing fancy going on there. I got the average of 4 scores. That's all I've done. Okay. And I'm going to take that out now. So I'm going to take 5 out of here, 5 out of here, 5 out of here, and 5 out of here. And then we're left with only the effects of A, B, and A by B, because we've removed the grand mean. So we end up with 4, 2, negative 2, negative 4. It's just arithmetic. I just subtracted 5. So with the grand mean removed, we can go on and look at the effects of A and B. You can double check that I removed the grand mean properly. That all sums to 0. I've taken out the mean. I've taken out 5 from each cell. Now that that's gone, it should be 0, the grand mean. And it is. Okay. So what I'm going to do now is I'm going to sum across A. So 4 and 2, and negative 2, and negative 4. So the average for B1 is 3, and the average for B2 is negative 3. Hey, look, the B effects sum to 0. And while I did make up these numbers, I can tell you that the only thing I did here was make sure I didn't have fractions. But you should be able to see that it would just work this way. So all the scores in B1 are elevated by 3. All the scores in B2 are depressed by 3. So let's take 3 out of B1, and let's take negative 3 out of B2.
Say that again.
We're going to take 3 out of B1, and we're going to take negative 3 out of B2. That's all we're going to do. Same thing as we did before, except now only they apply differently to B1 and B2. So I'm going to get what? 1, negative 1, right? And then 1, negative 1. Hey! Subtract 3 from all the B1s and negative 3 from all the B2s. And now we can find out what the average is for the A's. For A1, it's 1, and for A2, it's negative 1. So we're going to do the same thing as before for the A's. Now we're going to take 1 out of all the A1s and negative 1 out of all the A2s, and you can probably see what's going to end up with. We're going to have nothing left. We're left with absolutely nothing. That is telling us now there's no interaction, because if there was an interaction left, these would be non-zero. They would be non-zero. So there's just a mean and effects of A and B. There is no interaction effect. Now this is all hypothetical, obviously. But hopefully this illustrates the idea that you'd have no, in this case, no interaction. What you could do to prove it to yourself is you could graph it. That's the original numbers just thrown into the program numbers, actually, which just made a graph for me. Notice how there is an effective A, because A1 is higher up than A2 on average, and B1 is higher up than B2. There's an effective A and an effective B, but there is no interaction because the effect of A does not change depending upon the level of B. The lines are parallel, in fact. The lines are parallel. Questions? Before I go on and look at another one, do you have any questions? Good? So here's another example. A1, A2, B1, B2, so it's 2 by 2, 20, 0, negative 2, oh, sorry, negative 10 and 2. So we're going to first take out the grand mean. So that's going to be, let's see, 20 minus 10, but plus 2. So that's 12 divided by 4. It's 3. So we're going to take 3 out of each cell. So subtract 3, so you get 17 minus 3 minus 13 minus 1. Right? So now we're going to remove the grand mean. I don't know why that other thing disappeared. That was weird. And I just did that, and no, just the exact numbers I just said. Now you can do the A's first or the B's first, doesn't matter, but just pick one. I picked the A's. 4 and negative 4 is the sum, so that means the effective A1 is 2 and the effective A2 is negative 2. You know, it's interesting. Those are deviations from a mean. And if I sum those together, 2 and negative 2, and I squared them, 4 and 4 is 8, the sum of squares for A will be 8. That's actually how the sum of squares works. They just usually work with the means. We've taken the mean out to make it all from 0. We'll eventually get there. I'm just saying that you might be wondering where the sum of squares are and the mean square. Well, the sum of squares here is going to be, for A, is 8. Because it's 2 squared plus negative 2 squared. Which is 4 and 4, which is 8. So we're going to take 2 out of A1 and negative 2 out of A2. Yeah.
Where is the 2 coming from?
I'm dividing 4 by 2 because there's 2 observations that got me a sum of 4.
Oh, because that's just the
I
sum.
want the average
Not
effect.
the-
Yeah, it's the sum. It's not the effect itself. Yeah.
Okay.
Yep. Yep. You good? You look like you.
I thought I was, and then you asked, I realized I don't understand that.
Okay, what don't you understand?
Okay, so just the 2 thing one more time.
Right, so I'm just getting the sum of those 2 scores, which is giving me 4 and negative 4. But I want an average of the effect. So you've got 2 observations, you divide by 2. You get the average. Just like when you get the grand mean, you divide by 4 because there's 4 observations.
Oh.
Yeah, that's always the thing.
Yeah.
Somebody, I understand that it can be confusing, but then you go, oh, yeah. Right? Because I'm just getting an average. The average effect is plus 2 or minus 2 here, because we have 2 observations for each of those. Okay. So we take 2 out of the A1s and take 2 out of the B2s. And like I said, it's neat how they always sum to 0. They will always sum to 0. They can't not. If you were doing an example like this on a quiz, they have to sum to 0. If they don't, you did it wrong. It is impossible for them not to. The universe works this way. It really does. Like you can't come up with numbers where it wouldn't work out that things sum to 0. It can't be done because of the way you're doing this procedure. So I've taken the 2's out. 15, negative 1, 1. So go summing across A to get for B's. I got 14 and negative 14, or 7 and negative 7. Notice how the cells sum to 0, the grand mean is gone. And so do the columns, because we've taken out the effect of what happens to A. So it's gone. So if we've removed it, it's going to sum to 0. You can always check as you go along. So for B, we'll have B1 is 7 and B2 is negative 7. Or take 7 out of all the B1s and take negative 7 out of all the B2s. And we end up with this. There's stuff left over. I don't know why I did it like that. It's sort of ridiculous. Yeah. I don't know what I was doing there. So we have an interaction because the effect of, we've taken out the effects of A and B, yet there's still something left. So being at A1, B1 raises your score by 8. Being at A2, B1 depresses your score by 8. And then same thing down here except flipped around. Note how they sum to 0. Note how they sum to 0 down and across. Okay?
Can you just go back one slide?
I can go back. Let's do. Whoops. I think I went too far back. Here, right? And then whoops. Okay. So there? Is that where you want to go?
Yeah.
Okay.
Thank you.
Yes. So, in this case, we had 7 and minus 7. We're just going to take the 7 and the minus 7 out and see what's left. Sum of squares for B, out of curiosity. Let me just calculate. 7 squared plus minus 7 squared. Which is 98. Okay. Then we have the interaction. Because we have, it's because they're non-zero. Okay? So we have an interaction. The effects do sum to 0 in every possible way. If it was just zeros, we have no interaction. Zeros is nothing. Zeros mean there's no interaction. Now you could, this would be a bizarre thing to do, you could take out the interaction and you'd have zeros. Okay, let's take 8 out of that and then 8 minus 8 over here. I don't know why you'd do that. Sum of squares for interaction, by the way, is 8 squared plus 8, negative 8 squared plus 8 squared plus negative 8 squared. 256. Did that right? 64 and 64 is 128. Yes, 256. All those 8s sum together. All those 8s squared. Okay. So and if we graph this one, we'd see, wow, is that ever an interaction? It's not just the effect of A changes depending upon the level of B. In fact, the order of the effect changes depending upon the level of A here, doesn't it? At A1, B2's way bigger than B1. Or sorry, yes, B2's bigger than B1. And at A2, they're almost the same, but B2's a little bit bigger than B1. Completely switches. Completely switches. Questions so far? You might think, when would you get these kind of results? Well, think about it. This happens all the time. If you think about something like levels of processing, or retention interval. We'll go with retention interval. And we have different retention intervals here, 1, 2, and 3, whatever they are. And we had a memory test, which was just recall. It's going to look like that. So that's called a recall. And we had another memory test, which was word fragment completion, where you actually just fill in blanks if you see words before. And in fact, what you get in that case is that. Oh, look, it's an interaction. This happens all the time. We're dealing with pretty complex systems. We're dealing with living systems. Usually one variable doesn't do things on its own. Usually there's an effect it has on its own, but it also works with a whole bunch of other things. That's basically how it works with living systems. They just work that way. Okay, so how do we interpret this? It's kind of difficult to interpret main effects, that's just the effective A or just the effective B, in the presence of an interaction. I bet you, with our example here, with word fragment completion and recall, if we just looked at retention interval on its own, on average, the memory score goes down. But would you be comfortable saying that retention interval makes memory poorer with those results? Probably not, right? Because it'd say if the task is recall, yes. And think about what you're saying. If you're saying that retention interval affects memory if it's recall, you're saying the effect of one variable changes depending upon the level of some second variable. That's what you're saying in the abstract. So be kind of careful. It's not so bad with what's called an ordinal interaction. An ordinal interaction is where the order of the main effects is preserved. So let's go over here. It's probably easier for everyone to see over here. A certain level of decorum that involves erasing the board when your class is done. So let's say we had an experiment like this, we got a result like this. So it's A1, A2, we have that's a 2 somehow, dependent variable here, and so B1, and there's B2. There's probably an interaction there because those are not parallel lines, but I would feel pretty confident saying, I would be able to say that A2 is lower than A1, and that B1 is higher than B2. So I would be confident enough to interpret this by saying I have an effective A and an effective B and an interaction. Because that effect, the difference between B1 and B2 is bigger at A2. But I'm confident enough here that I can say that without hedging. I can talk about A, the effective A on its own. I can talk about the effective B on its own. That's something I can do. I feel perfectly happy doing that. That's called an ordinal interaction. Okay? This is when the order of main effects is preserved. On the other hand, we'll do this. And we'll do B1. And there's B2. There's probably an effective A there. Because all the scores at A2 are lower than the scores at A1. But can I talk about one of those effects without talking about another effect? I can't. I can't say that B1 is bigger than B2 because I at A1, but not at A2. So this one is called a disordinal interaction. So with a disordinal interaction, it's much harder to talk about main effects. In fact, you might want to just avoid talking about them altogether. Are they there? Yes. But can you interpret them? Without interpreting the interaction, without talking about the interaction, you can't. So it's probably impossible to talk about the main effects without talking about the interaction. So why do it? It seems to me at this point you say, no, I can't do that. And you'll see this a lot in papers when you read them. People will say there's a main effect of A and a main effect of B. Well, they'll say the variables are going to call A and B. And then they'll say there's an interaction, and they'll talk about the interaction. They won't really talk about the main effects. Because you can't. You can't talk about them without talking about the other variable. Remember, interaction is the effect of one variable changed depending upon the level of some second variable. Some people will say never talk about interactions or main effects in the presence of interactions. So people say that. I think they're being too conservative. I think in the example on the left, an ordinal interaction, I can't. But everybody's a little bit different. Like I said, if you have to tie yourself into knots by talking about when you talk about the main effects, stop doing it. And then usually you have to do that when you're in a disordered interaction. Whenever I get a notification, I keep thinking maybe there's been a trade in the NHL because the trade deadline's coming. I'm sorry, I'm checking. You know, it's actually important to me. This is just a way for me to get enough money to subscribe to NHL hockey games. That's all this is. And buy liquor. That's really all this is. And it's a calling. Oh, I was really hoping the music would start up. Oh, it was perfect. But no. Alas, no. So do you understand why this? First of all, you understand the notion that people have, a lot of people have, that you just don't talk about main effects in the presence of interactions. Because it's hard to. You know, A1's bigger than A2, but way bigger than B2 than there's a big one. So some people, as I said, more conservative in their way they do things would say, just don't do that. I would say if I can do it, I can do it here with an ordinal interaction. I can't do it with a disordered interaction. I can't well, I can't talk about the effect of A without mentioning B. I just can't. So I don't. Now, I have also heard people say you should talk about all the effects, but I think if I can't do it without twisting myself into knots, I'm not going to do it. Right. Questions about this so far? Yeah, let's do that. Do one more thing. So the sum of squares and degrees of freedom can be partitioned just like they were with straight up simple analysis of variance, one-way analysis of variance. So the model is again x equals mu plus alpha plus beta plus epsilon. You will remember that. I've said it a lot. I'm sure it's it. If you noticed the other day, I almost said that instead of saying x equals mu plus tau plus epsilon. Because I think in Factorial ANOVA, I guess. So, okay. Sum of squares total equals the sum of squares for A plus sum of squares for B plus sum of squares for AB plus sum of squares for error. So if we were to get more fancy, not even fancy yet. Let's think about what these things mean. Sum of squares for A is the square deviation of column means from the grand mean, as I said before, right? Now, I'm saying, but they're from 0. Yeah, that's because we took out the grand mean because it makes the arithmetic easier. But that's all they are. Sum of squares for B, of course, is squared deviations of row means from the grand mean. So, sum of squares for AB. sum of squares for AB, that's the interacting sum of squares, is the square deviations of cell means from what we would expect given the row and column means. This is that extra stuff that's left over when we've taken out the effect for rows and columns, or for A and B. So square deviations of cell means from what we'd expect given the row and column means. Sum of squares for error, which we didn't do, like I said, I just said let's just assume there's subjects in there and their means came out like this, are just square deviations of individual scores from their cell means. You can do that, it's just that we'd still be on the first example. It would just take forever. But it's the same principle. You would just figure out what all the individual scores were. Okay. So now we'll be precise with this. We'll do this now with actual notation. Sum of squares total, look, it's x minus x bar sub g. That's each score minus the grand mean. Sum of squares for A, sum of squares for B, sum of squares for AB, sum of squares for error. Those 3 summations. Well, why are there 3? Because I'm doing it inside each cell, and then I add that to each other cell, and I add all those up. I'm just summing 3 times. You don't have to, no one's ever going to make you do this. That would be ridiculous. No one does these by hand. Why would you do it by hand? It's insane. It's easy to do with a computer, so why not do it that way? There are big N minus 1 degrees of freedom in total. And any design has a finite number of degrees of freedom. It's going to be the number of observations minus 1. Now we're going to partition that out. This is there are A levels of A, so there's A minus 1 level of degrees of freedom for A. There's B minus 1 degrees of freedom for B. There's A minus 1 times B minus 1 degrees of freedom for the interaction. And then for sum of squares error, or within groups, if you want to call it that, it's A times B times N minus 1. I don't know where the A minus 1 went, I pretend it's still there. B minus 1 and A minus 1. Think about this. If we have a simple 2x2 design, if I say that the effect for A1 is 1, what's the effect for A2? If A1 was 1, A2 must be, yeah, I have 1 degree of freedom. I have the number of levels of A that I have minus 1. Let's make this just a little more complicated though. Let's make it a 2x3. So if all the A's went up, so if I went 1 minus 1, the final one would have to be 0. If I did 6, I think it was 6 minus 3 minus 3. I have the number of levels of that independent variable minus 1. For the interaction here, let's make it even bigger. B1, B2, B3, that's the worst looking 3. I'm just going to erase that even though no one's ever going to see it. Okay, how about 2 and 4 and I don't know, 6. And I don't know, how about another 2 here? Minus 4, minus 10, 14. Let's see, so that's going to be 2 and 6 is 8, so it's going to be negative 8. 2 and 4 is 6, negative 6. I had 2 times 2, B minus 1 times A minus 1 degrees of freedom. I could arbitrarily assign 4 values in that case. After that, the rest of them are fixed. Okay, so it's A minus 1 times B minus 1 degrees of freedom. How many degrees of freedom do I have here for within each cell? Let's say there's 5 people per cell here. So within each cell, how many degrees of freedom are there? 4. Then how many cells do I have? A times B. So it would be 3 times 3 times 4. Okay? So it's 3 times 2 times 4. A times B times n minus 1. Questions so far? We're going to stop here because this is a lot of stuff at once. And also because the break's coming and you should all go have a break. All right? Okay. So if you're watching this on the video, we just had a break of a week. And then we also had a snow day. Ha ha! So you missed it, internet loser. So, my viewers love me. But anyway, so we were talking last time about this factorial analysis of variance. By the way, does this look to anybody like a curling rink? Hurry! There's something on the board. That's what I'm doing. So, we have these, for some reason this is missing here, but that's going to be B minus 1, levels of B minus 1. So that's the degrees of freedom. So total number of degrees of freedom in any design is always the number of observations minus 1. And then you can partition that. So levels of A minus 1, levels of B minus 1. A minus 1 times B minus 1, and then A times B times little n minus 1. Little n is the number of subjects per group. Okay? And then on top, all these are basically are sums of squares. On top, mean square, degrees of freedom. On the bottom, so you get sum of square and mean square. So don't worry about the n times q, n times p. Theoretically, clearly it matters, and calculationally, which I don't think is a word, it matters. But the important thing to note is what is inside the brackets here. So you've got means for all the groups, all the A groups, like A1, A2, A3, whatever, minus the grand mean. The B's minus the grand mean. Individual scores. No, that shouldn't be that, actually. That should be, yeah. Rows, columns, and then we add the grand mean back in because you've taken it out, basically. The important thing is all these are just deviations from a grand mean. Okay? So, one of the things we want to look at, remember before we looked at the expected values of for a one-way analysis race, which was, remember the expected value of mean squared treatment was, anywhere, is there an eraser? Yeah, there is. So, with the sort of one-way analysis of variance, the expected value mean squared treatment is in essence treatment plus error, and the expected value of mean squared error is just error. Okay? So we could then take mean squared treatment divided by mean squared error, and what that allows you to do is sort of isolate the treatment effect. Okay? So, I have that written right there. Why did I do that? So yeah, we just divide mean squared treatment by mean squared error to find out if we have an effect. That's how it basically works with the one-way analysis of variance. We're going to do something exceedingly similar here for the factorial analysis of variance. So we have to have something for mean squared A, for mean squared B, mean squared A, B, and of course mean squared error. So we have to get what the expected values are, and they're not going to surprise you. So the expected value of mean squared A is variance due to A, alpha, plus epsilon. The expected value of mean squared B is beta plus epsilon. You can probably guess that the expected value of AB is alpha beta plus epsilon. And of course, the expected value of mean squared error is error. Okay? There might be a typo in the notes. If I haven't updated it, I know I updated this. If it looks like that, it's fine. So ignore it. So fine, we're going to divide A by error, B by error, AB by error. That isolates the effect of A, the effect of B, and the interaction effect. Easy. Right? So it's a really simple thing to do. All these, we're going to do 3 f-tests in one analysis, but we're always dividing by the same thing. We're always dividing by mean squared error. Now, however, whenever I say something's easy, there's always a however. Those expected values actually only work when you are only interested in those very levels of A and B and no other levels. And you're thinking, what? How could that be? How could it be that what I'm interested in affects math? That's not actually what it is. It sort of works the other way. If you had randomly chosen the levels, then you could generalize to all possible levels. Does that make sense? Okay. Let's think of it this way. If I want to generalize to people, I can't use this classroom. This is not representative of the humans. Right? There's more women than men, there's more white people than anything. That's not humanity. If we randomly choose people, then we can generalize to all people. Does that make sense? Well, why wouldn't that be also the case with levels in an experiment? Well, in fact, it is. So if you're doing an experiment, technically, you should randomly choose the levels of the variable you want. So let's say you want to look at retention intervals in a memory experiment. And when you do something like that, you in fact, very often, how I've done this, geez, there's always things in my way. Okay. It could also be because I can't see, but I think there's things in my way all the time. So let's say you choose like 5 minutes and 1 hour and 24 hours. The scale's really off, but whatever. And you get that. Let's see that. What you're going to probably do is draw a graph that looks like this. And what's the implication? That I can look at along the x-axis and go, oh, it'll be that or that. We connect the dots. But you really shouldn't do that. We all do it. But you really shouldn't do it. Was it my little dance of thanks? That's what was fun. It's something that we all do, but we actually shouldn't do. If we want to talk about all the possible values between 5 minutes and 24 hours, we should have a random number generator pick 4 or 5 levels. That's going to be hard, and it's actually not going to be something we're ever going to do. So, the expected values I just showed you, those very sensible ones, are only true if those are the only values of a variable you're interested in. It's called a fixed effects model. Okay. So for a fixed effects model, those expected values are true.
So the dots are true, but the lines.
The lines, putting that line in there, you're actually lying. What you're doing is you're saying to people, oh yeah, you could also say obviously that in between there and there you get that, and you don't know that.
Okay.
You don't know that. It's probably true. The world almost certainly works like that. There have been enough experiments on retention interval in memory that I can tell you that that's what a freaking forgetting curve looks like. Cross species, I mean, but from your one experiment, you probably can't make that conclusion. What if we did randomly choose the levels? What happens then? If we actually truly randomly choose them, then we add another, I don't want to say source of variation because that means something very technical. We're adding There's a new wrinkle. Let's just say that. So in fact, a random effects model where we've randomly chosen the levels of A and B, whatever A and B are, the expected value of A changes to alpha plus alpha beta plus epsilon. The expected value of B changes to beta plus alpha beta plus epsilon. The expected value for the interaction, thankfully, stays the same. The expected value for error stays the same. So in this case, if we have randomly chosen our levels, we divide mean squared A by the interaction mean squared B by the interaction mean squared, and AB by mean squared error. So the way we actually do the statistical test changes. Weird, right? But actually, when you think about it, there's this extra bit of randomness that the math is taking into account to figure out this expected values. That's why the expected values change. It's crazy. What if we have... Why did it do that? Okay. What if we have a mixed model? A is fixed and B is random. Do that. It looks like this. Expected value for mean squared A is A alpha plus alpha beta plus epsilon. Expected value for B is beta plus epsilon. Alpha beta is alpha beta plus epsilon. And expected value of mean squared error is still error.
So if A is fixed and B is random, why is A the one that has the alpha beta added to it?
Math.
Okay.
Yeah. It's and that's one of those that's beyond the scope of this course
Okay.
discussions. I know that that looks wrong. Yeah, it's completely counterintuitive,
Yeah.
but it's right. Believe me, when making up the notes for doing this course years ago, I reread all my old notes from graduate school. I reread two chapters in a book thinking, I know I must have this wrong. No, I don't. The world's weird. So that's called a mixed model. That's a mixed model. Okay. So, with a random effects model, we are assuming that all the levels of the random factor were truly chosen at random, or something approaching random. Okay. That we didn't fix them. It's probably a better way to say it, if you want to get into sort of practicalities, is that we didn't fix the levels. It's not going to happen that often. This is not going to happen that often for the kind of work that any of us here do or will do. So that'd be randomly selected independent of each other. It's an extra assumption that's thrown in with any random effect. What we're usually doing is a kind of random sort of mixed model, kind of sort of. We typically are doing a fixed model. That's the analysis we do. That's the default of anybody's analysis, and that's what 95% of the people who use analysis of variance actually don't even know this stuff. Because they learned it at some point and forgot it, or they didn't pay attention, or they never learned it. So people don't actually tend to even think about this stuff. The people who think about this stuff tend to be really into statistics or actual statisticians. When is this going to matter? There are times when you might do this. Let's say, I don't know, I think the book has an example, I think, or is it another book, I don't know, of testing tire wear. Why do you do that? Well, you're a tire company. And you have people get these tires, different compounds of rubber, and you test the wear. And let's put city in there as another factor. Right? So you can have 5 levels. It could be here, it could be Vancouver, it could be Quebec City. Let's try to think of various weather patterns in the country. Windsor, and count. Did you randomly choose those? Probably not, but do you want to generalize to all possible Canadian driving conditions? Yeah, you do. And those choices you made, while not random, are kind of like how we choose subjects in an experiment. Right? Typically what we do is say, you want to be in my experiment? Please sign the thing, and then a chance of winning a $3 gift card. Now please do the circle effect. You're done. We don't choose those people at random, but because typically we're talking about sort of fundamental properties of things, so it's like, well, while that doesn't represent humans, we can certainly say that everybody's cognition works roughly the same, we're cool. Same sort of thing here. We didn't randomly choose the cities really, but we didn't just pick those cities and no others and only care about those cities. So in that case, you might use a mixed model. So it shows up sometimes in kind of field work, or it should. Very often it doesn't. So people make some mistakes with those kind of things in their analysis. And usually at their own, they miss effects that are there. I've reviewed a paper for a journal a couple times and seen that this should be a random effects model. They just, you see the analysis there and say, oh, just divide that by that. And I tell people, no, you have a significant effect. You just did your math wrong. So did you really randomly select the levels or do something similar? I like to think of it again the same way we select subjects for an experiment. If you did that, then yes, use the random effects calculations. Any other time, just use the fixed effects ones. Okay. It's a strange thing to think of, but it actually is a real issue. And it will come up again, and it will do something, it'll allow us to do something very cool. So, well, I think it's cool. You guys probably don't care. Because you guys are mean. A lot of you. Okay. Don't know what that extra bullet point was there for. So your analysis variance summary table looks something like this. A by B, and error. There's the degrees of freedom. There's your mean squares. And there's the F, how you calculate the Fs. Of course, that's for fixed effects only. But you will hardly, I bet, anybody in here who goes on and does science for a living, I bet you never use a random effects model or a mixed model. It's just so vanishingly rare to use. Because usually you aren't randomly choosing places. Or even sort of quasi-randomly. Again, are you choosing it the same way we choose subjects for an experiment? That's sort of the rule of thumb I would use. And if you are, then fine. In the crazy field experiment that I'm doing along with Jen Foot right now, we have like 3 different locations for these feeders, for clusters of feeders. We didn't really randomly choose them, and also because the weather's been so bad, I think what we've determined is birds don't like bad weather, which is not really groundbreaking. It's not groundbreaking. But, and we're not going to use analysis variance anyway. But if I was, in that case, I'd probably say, yeah, we should probably analyze that way. All right, questions so far? I know this is a little weird. It's a little wild. What's different? Okay. Hey, let's make the design bigger. So let's shift gears from something strange and esoteric, frankly, to something sensible. Something you might do, something quite possibly that you will do. Something that if you go to the psychology/biology honors thesis conference in March, which you should. Yeah. All of us together talking about life science. It's going to be awesome. You will see designs that have 3 independent variables. They're never from my students. I don't let people have more than 2. I just tell them, can you think in 3-dimensional graphs? Good, you can do it. No, you can't. can think about three-way interactions, but it's hard for them. What do we have here? We got ABC, G1, G2, G3, 4. So one group, 2, 3, 4, 5, 6, 7, 8. We've got, this is a 2 by 2 by 2. Okay? Interpreting these kind of interactions can be difficult. So you got this is a 3-factor design. So now you have 3 main effects, alpha, beta, and gamma, or ABC. You have 3 two-way interactions, A, B, A, C, and B, C, and you've got a 3-way interaction, A, B, C. I'm not going to go into expected values for these things because we'll be here for the end of forever. A 3-way interaction is when the 2-way interactions change depending upon some third variable. Okay? So it's when the 2-way interactions change depending upon some third variable. So you get something like this. Okay. So think about a 2-way interaction. Something like that. You go, okay, yeah, that's a 2-way. That's a beautiful 2-way interaction, right? The effect of B changes depending upon the level of A. Well, let's make it now a 3-way interaction. Let's say this is C1. And here are the results at C2. There's 2 different 2-way interactions. Those 2-way interactions change depending upon the level of C of a third variable. Okay? This is not an uncommon kind of design, 2 by 2 by 2. You'll see, like I said, if you go to the honors, the Life Sciences and Environmental Physics Conference, you will see 3-factor designs. Almost certain of it. Think about real-world examples. 2 kinds of memory tasks, implicit and explicit. One, what's explicit? That's like I have you recall words. Implicit is filling in blanks. Right? And in that, what happens is the implicit is steady, and the explicit drops. That's a 2-way interaction. What's the 3-way interaction? I don't know. One group is normals, and the other group have hippocampal lesions because they've bumped their heads or they've got, they've had a stroke. Their implicit memory is normal, and their explicit memory basically doesn't exist. That's a 3-way interaction right there. The 2-way interaction between time, that's the forgetting part, and memory test type changes depending upon if they have hippocampus or not. It's a very common kind of thing. It's not uncommon at all. Okay. Questions about that to understand the idea of 3-way interaction? Yeah? Okay. So the model's a little different now. Now the model is x equals mu plus alpha plus beta plus gamma plus alpha beta plus alpha gamma plus beta gamma plus alpha beta gamma plus epsilon. Epsilon. Right? A, B, C, A, B, A, C, B, C, A, B, C. Error. So just the model gets bigger, that's all. So what are you doing here? You're actually testing. You're going to have an A effect, a B effect, a C effect, an AB interaction, an AC interaction, an BC interaction, an ABC interaction. So now you're doing 1, 2, 3, 4, 5, 6, 7 F tests in one analysis. 7 F tests in one analysis. Wow. It's totally doable. Again, when you think of an example like the one I gave, there's all kinds of other things like that. Think about in learning, when you might look at, again, time is one of the variables, task, and sex differences, right? So, in fact, oh yeah, I got it. Again, they drew it on the board, and I have one right here. So we have, that's an ABC interaction. The two-way interactions change depending upon the level of the third variable. A 27-way interaction is the 26-way interactions change depending upon the level of some 27th variable. I've never seen one that big. I have seen four-way interactions. So now you're going to have D1 and D2, so you have this panel and another one, and it's now be the three-way interactions change depending upon the level of the fourth variable. I don't like experiments like that because I find it very difficult to think in 4 dimensions. It's hard. 3 is okay. 2 by 2 by 2, or 3 by 3 by 3, or 6 by 6 by 9, I don't care. But when you start to get into more than that, I find it difficult. So, okay. These kind of designs, what are some good things about them? These factorial designs. We can study interactions, and so many theories in behavioral sciences generally, in life sciences really, generally involve interactions, two things coming together, right? So much of what we talk about involves two variables acting together, doing more than they would do on their own. Once you've done this a few times, it's actually pretty easy to interpret these things. And again, when you think of a real-world example and you have a graph in front of you, you say, oh, I see what you're talking about. So they're not horrible to interpret. Of course, there's got to be a downside. Is it a fixed model, a random model, or a mixed model? Now, again, as I said, no one really cares about this. No one pays attention to it. But there are times when you should, and it will change your analysis. It's going to be rare in the kind of work that most of us do. Also, these things can get very big very fast. Right. So, if we did let's throw in D, right? So we got A, B, C, D now. So we got A, B, A by B, C, C by A, C by B, C by A by B, D, D by A, D by B, D by A by B, D by C, D by C by A, D by C by B, D by C by A. So now you're doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now you're doing 15 F-tests with one design. And that's going to double in size if we throw in a fifth factor, right? A plus 1. Wow. So this can get exceedingly complicated. That starts to get complicated to interpret, to keep straight in your head, frankly. Now, if you know exactly what you're expecting, and all you're going to care about is a 4-way interaction, I don't. Actually, an old prof of mine, in fact, he taught me basically this course when I was undergrad at Western. He had this whole thing about sex and handedness and spatial task, and it was one other variable. And all he expected was a pure 4-way interaction, and he got it. But it's the only time I know of that happening, and I can't even remember the example. He was quite a guy, by the way. He didn't have an undergrad degree, just a PhD. We would always look at the beginning of the year, but your profs, you'd always look and you'd say, oh, because it would say we're in school. I went up to him, I said, Dr. Hirschman. He's like, you can call me Richard. Okay, Richard. Why are your undergrad degree's not listed? He goes, well, I kind of dropped out. Really? Yeah. It's the 60s. So it's And but I was working on factor analysis. I don't know if you know what factor analysis is, but it's a really complicated statistical thing. And I found a mistake in it, so I corrected it. Oh, just did that as an undergrad. Yeah, I wasn't going to school anymore, but I thought I'd get it published, so I sent it off to a journal, and they said, "This is a horrible journal article, but it'd make a good PhD dissertation. Come take classes with me." Like this, it was at Berkeley, of course he was. And it'll give you a PhD. So that's how I got my PhD. Okay, so that's, by the way, that's not a career advice. That's not how you do it. You don't do research for 3 years, do a lot of acid, drop out of everything, and go, I should publish that stuff I wrote. And then they'll give me a PhD. The world was different then. I used to quote Dylan in a class like this and say, "So does this remind anybody of a Dylan song?" Well, I don't know. It's like you know that something's happening, but you don't know what it is. That's him talking about four-way interactions. He was amazing. Taught me a lot, that guy. So, that's the one example. The guy who doesn't have an undergrad degree is the only time I ever think of someone looking for a pure four-way interaction. I remember showing it to the class, and we're all like, okay. So, that's the downside, is they can get very big very fast, and then it becomes very difficult to interpret. If you, let's say you're looking for a four-way interaction, you find it, that's great, but then you find a bunch of main effects, and hell, now you're screwed. Like if you want just pure four-way, that's great. All right, questions on this? Because I can show you some SPSS in a moment.